In this module, we shall discuss non-parametric tests for homogeneity. We start from Wald-Wolfowitz Runs test and give some properties like distribution, summary measures, large sample distribution, and of course a large sample test. Then we shall introduce Kolmogorov-Smirnov procedure for a homogeneity hypothesis and also discuss some properties. Lastly, we show how theory of runs can be used to check whether the observations are coming in a random manner or not. We have already discussed single sample hypothesis testing problems like sign test and Wilcoxon sign rank test and goodness of fit tests. Two sample hypothesis testing problems for location family like Mann-Whitney U test is also discussed, and we have also discussed some properties of this test. Now in this module we shall discuss homogeneity hypothesis. Suppose we have observations xi, I from 1 to small n, and observations yj, j from 1 to small n, and these observations are independent from distributions f and g respectively. Then the null hypothesis can be expressed as fx equal to gx for all x. The most general two-sided alternative is fx not equal to gx for some x. Next, we shall discuss how the arrangements or say pattern of the arrangement of the observations can be used to deduce a test. For the test of general alternative, we can use the arrangement pattern of the observations to derive a meaningful test. Under the null hypothesis, the two samples can be regarded as a single sample of size capital N equal to m plus n from a continuous but unspecified population. Then we have n choose n equally likely configurations of m x observations and small n y observations. The arrangement pattern gives information about the closeness of the underlying populations. For example, if the observations are well mixed, then we could think of identical populations. However, if there is a pattern in mixing, a deviation from the null is natural. Many statistical tests are based on the pattern of mixing in the combined arrangement of capital N observations. So, next we introduce the runs. A run is a sequence of similar symbols preceded and followed by a different symbol or by no symbol at all. For example, consider 4 x observations and 3 y observations arranged in increasing order of magnitude in the following way: x, then y, then again x, then y, and then lastly x. Then we have a run of 1 x, then a run of 2 y's, then a run of 2 x's, a run of 1 y, and lastly a run of a single x. The run length of the first run is unity, that of the second is 2, and so on. As another example, consider 3 x's and 3 y's arranged in increasing order of magnitude in the following way: x, then y, then again x, then y, then again x, then y. Then we have a total of 6 runs, but each of length unity. So our test, that is Wald-Wolfowitz Runs test, is based on these runs. Runs test is based on the total number of runs in the combined arrangement of n x's and m y's. If the two samples are from the identical populations, the observations are expected to be well mixed. Thus, R, the total number of runs, is expected to be too large. On the other hand, if the underlying populations are different, observations from different populations tend to be separated. Hence, R is expected to be too small in such a case. Thus, small values of R are indicative of the different populations. So, R is only a measure of deviation from fx equal to gx for all x. It does not differentiate between whether y is stochastically larger than x or x is stochastically larger than y. For example, consider the configuration x, 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 that is 4 x's in a row and then 3 y's in a row. Then the number of runs R in this case is 2, but all the observations are less than Y observations. This might indicate that Y is stochastically larger than X. Next, consider another configuration, that is 4Y in a row and then 3X's in a row. Then again, the number of runs is 2, but the configuration indicates the possibility that X is stochastically larger than Y. Next, we shall derive distribution of R. Assume that fx equal to gx for all x. Suppose the x observations are indicated by x's and y observations are indicated by y's. Under the null hypothesis, we have n chosen equally likely configurations of mx's and ny's. Suppose R1 is the number of runs of x's and R2 is the number of runs of y's. We shall first obtain the joint distribution of R1, R2 and then find the distribution of R, that is the total number of runs. In addition, we shall obtain the first few moments of R. So we start with the distribution of the joint distribution of R1 and R2. First of all, note that the observed values of R1 are starting from 1 up to small n, and observed values of R2 starts from 1 up to small n, but R1 and R2 cannot differ by more than unity, because then two runs with the same symbols have to be adjacent, which contradicts the definition of runs. If R1 equal to R2 minus 1, the arrangement starts with a run of y's, and for R2 equal to R1 minus 1, the arrangement starts with a run of x's. However, if R1 equal to R2, then the arrangement starts with either a run of x's or a run of y's. Thus, we define a function C R1 R2, which is 0 if modulus of R1 minus R2 exceeds 2, equal to 1 if the difference R1 minus R2 or the absolute difference between R1 and R2 is 1, and is defined as 2 if the absolute difference between R1 and R2 is 0. Now, we shall derive the joint distribution of R1 and R2, where this small r1 indicates the observed value of capital R1 and small r2 indicates the observed value of capital R2. Under the null hypothesis, each of the m plus n chosen arrangements of mx's and ny's are equally likely. Now, to get R1 runs of x's, we need to put R1 minus 1 bars in available n minus 1 positions, and for each such choice, if we put R2 minus 1 bars in available m minus 1 positions, we get R2 runs of y's. Then the total number of ways of getting R1 runs of x's and R2 runs of y's is C R1 R2 multiplied by n minus 1 choose R1 minus 1 multiplied by m minus 1 choose R2 minus 1. Thus, we have the following joint distribution, that is the number of ways whole thing divided by m plus n choose n. Next, we shall obtain the marginal distributions of R1 and R2. It is well known that the marginal distribution of R1 is nothing but the summation over the joint distribution of R1 and R2, where the summation being taken over the all possible values of R2. After a little algebra, one can find this marginal distribution or marginal PMF of R1 as n minus 1 choose small r1 minus 1 multiplied by m plus 1 choose R1 whole thing divided by m plus n choose n, where R1 ranges from 1 up to small n. In a similar way, we can obtain the marginal distribution of R2 as m minus 1 choose R2 minus 1 multiplied by n plus 1 choose R2 whole thing divided by m plus n choose n, where R2 ranges from 1 up to small n. Next, we shall obtain the distribution of R, that is the distribution of R1 plus R2. Note that here R1 and R2 are not independent. In fact, they are dependent and they have a joint distribution. So, probability R1 plus R2 equal to R is nothing but the summation r1 from 0 to small r, joint probability of r1 equal to small r1 and r2 equal to r minus r1. But for even r, the only possible value of r1 is r by 2. Thus, this probability, that is probability r1 plus r2 equal to r, comes out as twice n minus 1 choose r by 2 minus 1 multiplied by m minus 1 choose r by 2 minus 1 whole thing divided by m plus n choose n, where r ranges from 2, 4. However, for odd r, r1 is either r minus 1 by 2 or r plus 1 by 2. Then we get in a similar way that the joint distribution as n minus 1 choose r minus 1 by 2 multiplied by m minus 1 choose r minus 3 by 2 divided by m plus n choose n plus n minus 1 choose r minus 3 by 2 multiplied by m minus 1 choose r minus 1 by 2 whole thing divided by m plus n choose n, where r takes only odd integer values, that is r is 1, 3, 5 up to the set of odd integers. Next, we shall obtain the moments of r1 and r2. First of all, we discuss a lemma. The lemma gives that for any a, b and k, the summation I from 0 up to minimum of a and b minus k, a choose I multiplied by b choose k plus I equals a plus b choose a plus k. The proof is very well known and can be found in any usual textbook, so we are not giving details. The proof is very well known and can be found in any usual textbook, so we are not giving details. We shall find the moments of r1 and r2 from the factorial moments, and using the lemma just discussed earlier, the factorial moment of r1 can be obtained as given in the slide in terms of m plus n minus g choose m divided by m plus n choose n, and in factorial notation m plus 1 upper g. And in a similar way, the factorial moment of r2 can also be obtained. Then once you get the factorial moments of r1 and r2, we can take just g as 1 to get expected value of r1, which comes out as n times m plus 1 divided by m plus n, and in a similar way we get the expected value of r2 as m times n plus 1 divided by m plus n. Thus we get the expected value of the total number of runs as 1 plus twice mn divided by m plus n. Similarly, for getting the variances, we take g equal to 2 and get the factorial moment expected value of r1 into r1 minus 1, and using the relation that variance of r1 equal to expected value of r1 multiplied by r1 minus 1 plus expected value of r1 into expected value of r1 minus 1, we get the variance, and in a similar way the variance of r1 and variance of r2 can be obtained. However, r1 and r2 are correlated, so the sum of the variances of r1 and r2 is not the variance of r1 plus r2. So using some little algebraic manipulation, we find the joint factorial moment of r1 minus 1 and r2 minus 1, and using some expressions we get the desired expression. Now to obtain the variance of r, if we put g equal to 1 and we get the expected value of r1 minus 1 multiplied by r2 minus 1 as n minus 1 multiplied by m minus 1 multiplied by m plus n minus 2 choose n whole thing divided by m plus n choose n. Thus, using the relation that variance of r equals variance of r1 plus variance of r2 plus twice of r1 r2, we get the desired expression of variance. If we assume that n by m plus n tends to lambda, where lambda is a proper fraction, then we have the following approximation that expected value of r divided by m plus n equals or approximately equals twice lambda into 1 minus lambda, and variance of r divided by square root of m plus n equals 4 lambda square multiplied by 1 minus lambda whole square. Now we shall give the form of different tests using the total number of runs. From the intuitive justification, we reject the null hypothesis if r less than c for some c satisfying probability r less than c evaluated under the null hypothesis is less than alpha. Since we have obtained the large sample distribution of r and we find that under the null hypothesis, if minimum of mn tends to infinity such that n by m plus n tends to lambda, then r star, that is r minus twice capital N lambda into 1 minus lambda whole thing divided by twice lambda into 1 minus lambda multiplied by square root of n converges in distribution to a standard normal distribution. Then the large sample distribution of or a large sample distribution of r star can be used to get a large sample test, and a large sample test rejects the null hypothesis if this r star is less than minus of tau alpha. Next, we come to the homogeneity problem. We have already observed that run test is insensitive to stochastic alternatives. The most general two-sided alternative is fx not equal to gx for some x. The one-sided alternatives are actually stochastic alternatives like fx greater than equal to gx for all x with strict inequality. The one-sided alternatives are actually stochastic alternatives like fx greater than equal to gx for all x with strict inequality for some x, that is y is stochastically larger than x, or fx less than equal to gx for all x with strict inequality for some x, that is x is stochastically larger than y. If we can measure the discrepancy between fx and gx, tests for one and two sided alternatives can be derived. So we now derive or give some idea about the test based on empirical distribution function. From the theory of U statistic, the empirical distribution functions fnx and gmx are the U statistics for the estimation of dx. If f equal to g, there should be a good agreement between fnx and gmx for all values of x. Some overall measure of discrepancy between these functions is then a natural test statistic. Then, just as in goodness of fit problems, we use the statistics supremum over x fnx minus gmx or supremum over x gmx minus fnx. These statistics are nothing but the Kolmogorov-Smirnov distance function measuring the discrepancy between two continuous distribution functions. Now, we shall give the critical region for Kolmogorov-Smirnov test. Consider the alternative fx greater than equal to gx for all x. Then our statistic is dnm plus, which is defined as supremum over x fnx minus gmx, and we reject h naught if dnm plus is too large. Similarly, for other alternatives we can get similar type of tests. Next, we shall discuss that the Kolmogorov-Smirnov distance function and the corresponding test is actually non-parametric. Note that this dnm is defined as supremum over x of the absolute value fnx minus gmx. Now, if f equal to g, then consider the new sets of data fxi I from 1 to small n and gyj j running from 1 to small m. Note that fnx and gmx does not change for the new set of data. Now, the transformed data observations from a are the observations from a rectangular 0-1 population. Thus, dnm can be looked upon as a function of order statistics from rectangular 0-1 population. Hence, the distribution of dnm under f equal to g depends only on m and n. Thus, tests provided by the Kolmogorov-Smirnov statistic are exactly non-parametric. Next, we shall just discuss the consistency of Kolmogorov-Smirnov test, and we note that this Kolmogorov-Smirnov test is a consistent test because fn minus gm is a consistent estimator for f minus g. Next, we shall discuss an interesting application of Runs test, which is known as run test for randomness. We start with a real life example. Suppose the students entered a lecture theatre in a certain order. Then it is of interest to know whether students of the same gender come in together. If we denote male students by capital M and female students by capital F, then we get a sequence of symbols M and F. Naturally, well-mixed symbols tend to contradict that the students of the same gender come in together or they enter the lecture theatre in a random fashion. Any pattern in the symbols possibly indicate lack of randomness. Thus, our null hypothesis in this case is the randomness, and the alternative is naturally lack of randomness. The arrangement of M and F gives a number of runs of these symbols. If the number of runs is too few or too large, some pattern is expected. Therefore, a contradiction to the random pattern is expected, and hence we reject the null hypothesis in such a situation. So, if we have n data, n observations xi, that is data, from a continuous population fx, then the null hypothesis can be expressed as that x1, x2, xn is a random sample from some continuous population. However, the alternative, that is lack of randomness, does not specify any particular pattern. Now, to dichotomize the data, we use some statistic t based on all the observations. If we put the symbols L and U as the observation is lower or greater than t, we get an arrangement of two symbols. Naturally, we reject the null hypothesis if the total number of runs is too small or too large. We have thus discussed runs test and Kolmogorov-Smirnov test. We have seen that these tests are distribution free. We have also discussed some properties of these tests. Finally, we have seen how theory of runs can be used to judge whether observations are actually coming in a random fashion or not.